Hi, in today's class, we will discuss the concept of Earth's magnetism. Now, we know that actually the concept of magnetism came when, as you all know, some shepherds went to a hill their stick got stuck, something like that you have learned in lower classes as a story. Now, what is that itself shows that Earth has got a magnetism. And similarly, if you just freely suspend a bar magnet, you know that it always tends to align in the north direction. In Malayalam, we used to say vadakku nokki yantram, like magnetic compass needle. Now, what is Earth's magnetism? What is the cause of Earth's magnetism? The cause of Earth's magnetism is believed to be, it's not still clear, it is still mysterious, I have to say. But it is believed that the cause of Earth's magnetism is what is because of an effect called dynamo effect. As we all know, the core of the Earth has an extremely high temperature. Their metals are in the form of molten ions. Now, as a result of the heat, this will produce convection currents, and we know that convection currents will produce magnetic field. Electric current will produce magnetic field. So, what is dynamo effect? Dynamo effect is believed to be the cause of Earth's magnetism, and we can say dynamo effect as it is the effect which is caused by the currents due to the convection effects of molten ions inside the Earth. Now, Earth has got a geographic axis. This is geographic north, and this is geographic south. It has also got a magnetic axis, and this is magnetic north and this is magnetic south. Now, this is the angle between. So, just please understand this, because when it comes to the idea of declination, you may tend to mistake. That's the reason why sir is saying. So, actually, this angle theta, the angle between the geographic axis and magnetic axis is around 11.3 as given in NCERT, but I think it is now less than that value because it keeps on changing. So it is 11.3 degrees as what it is shown by given in the NCERT book. This is the magnetic north, this is the magnetic south. Then you may tend to say, sir, this is wrong, because in lower classes we have studied that this is the north pole of the Earth's magnet and this is the south pole of the Earth's magnet. So, what I have to say is that, okay, I agree to that point. But, actually, in what respect I agree is that the magnetic field is directed from likewise to likewise, I will say. That is where everyone says, if you treat Earth like a bar magnet, in that situation, north pole is located here, south pole is located here. But what is the convention of north pole, magnetic north pole and magnetic south pole? So, what is magnetic north? Magnetic north is the north pole. It is the north pole denoted by a freely suspended magnet. It is the north pole denoted by a freely suspended magnet. Then what is magnetic south pole? So this is a convention of dividing the magnetic north pole and magnetic south pole. It is the south pole denoted by a freely suspended magnet. So please understand this idea clearly. It is the south pole denoted by a freely suspended magnet. So magnetic north is the north pole denoted by a freely suspended magnet, and magnetic south pole is the south pole denoted by a freely suspended magnet. And please understand that the magnetic field lines outside the Earth are from magnetic south pole to magnetic north pole. Okay, this is the first idea to understand. Actually, I repeat that sentence once more. Outside Earth, the magnetic field lines are directed from magnetic south pole to the magnetic north pole. Moving on to the next concept, that is regarding magnetic meridian and geographic meridian, I think. Okay, so let me consider this. So let me consider, okay, before magnetic meridian, I will consider geographic meridian. That will give you a clear picture. Okay, this is Earth, I am saying. I need to change color. That I do. This is Earth. This is the north pole of Earth. And this is the south pole of Earth. North pole and south pole. Now I want, suppose that I am standing here and I want to construct a geographic meridian. Geographic meridian. I want to construct a geographic meridian. Okay. Now what I will do is that, okay, suppose treat it like a watermelon and I want to find out a geographic meridian. So what is geographic meridian? It is a vertical plane. I repeat, it is a vertical, it is a vertical plane that contains what? It's a vertical plane that contains geographic north, geographic south, and the place under consideration. And the place under consideration. So it's a vertical plane that contains geographic north, geographic south, and the place under consideration. That means if I want to construct a geographic meridian, means take a watermelon or take what I am saying, a lemon. Now consider the two parts, these two parts, north pole and south pole. Using a pen, please put a dot at some point. Take a knife and cut that lemon through that point. Cut the lemon through that point. So diametrically opposite. Now the plane of the lemon part that you see is what is called the geographic meridian. Which means, so if you cut this one, you will have something like a plane which is passing through this point this way, right? Now here you got a plane something like this, and this plane is called what is called a geographic meridian. It's a vertical plane. You are cutting like this. So it is at that place. It is at that place. This is what is called a geographic meridian. It is a vertical plane that contains the geographic north pole, the geographic south pole, and the place under consideration. It's a plane, vertical plane that contains the geographic north pole, geographic south pole, and the place under consideration. This is called the geographic meridian. Now this is the point P I am taking. Sorry. This is the point P I am taking. So this is the geographic meridian passing through that point P. Geographic meridian through the point P is represented by this plane. Then what will be magnetic meridian? So second thing I am going to do is I am going to teach you what is called magnetic meridian. Okay. Now what I will do is first of all I will just take a copy of this one. Now here I am going to make only two corrections I will say. One is magnetic north. The other one is magnetic south. magnetic south and is placed under consideration. See here. So what is magnetic meridian? It's a vertical plane that contains magnetic north pole, magnetic south pole and the place through which we have to take the meridian. Now in this case, where is magnetic north pole? So let me take, I am going to show the magnetic axis also. This is magnetic north, this is magnetic south. Now as per NCRT, this side is 11.3. Okay, now let me make the meridian. Now I am going to rotate it. Okay, approximately I understand this. Now this is the intersection. Now this is what is called a magnetic meridian. So this is called a geographic meridian and this one is called a magnetic meridian. Now let me ask you a question. This side is 11.3. Can you say this side also is 11.3? Will these two angles be equal? Will these two angles be equal? So actually I will tell you that is a big blunder if you say they are equal, because this will vary from place to place. Let me take this angle as alpha. Now the question is, how will you define alpha here? How will you define alpha in this case? So you got the definition of geographic meridian and magnetic meridian. Now my question, what is alpha here? Alpha is an angle. What is alpha? What is angle alpha represents here? This angle is alpha. Obviously this angle is also going to be alpha because they are vertically opposite angles. My question is, how do you define angle alpha? Angle alpha. Alpha is the angle between what? The geographic meridian and magnetic meridian. Alpha represents the angle between geographic meridian and magnetic meridian. So we call it by the name declination. Sorry. This is called a declination or variation. The angle alpha is called declination or variation, and we can define angle alpha as it is the angle between. So alpha is the angle between what? Magnetic meridian and geographic meridian. So angle alpha is the angle between the magnetic meridian and the geographic meridian. It is the angle between magnetic meridian and geographic meridian. Now, if so, alpha will vary from place to place. Alpha will vary from place to place. The angle alpha will vary from place to place. Now, there are certain places where alpha is equal to 0. There are certain places where alpha is equal to 0. Such places are the lines, or there are certain lines where geographic meridian and magnetic meridian coincide. So lines where the geographic and magnetic meridian coincide are called isogonal lines. Now for example, I will show you, this is geographic north, this is magnetic north. So this is magnetic south, this is geographic south. Okay, one more thing I will say. What is isogonal line? I didn't say properly. Now if I take a point A here, if I take a point B here, now we can see that this is nothing but magnetic meridian, this is nothing but geographic meridian for both of them. So for all points on this plane, all points on this plane, you can see that the declination will be 0 because magnetic meridian and geographic meridian are coinciding. So I am saying this is magnetic meridian, same is the geographic meridian because they contain, so this plane contains magnetic north, magnetic south, geographic north, geographic south, and place under consideration, right? So now if I join, okay, this is joined, this is joined, sorry, this is joined, this is joined, this is joined, this is joined. Now what are isogonal lines? Lines joining the places of same declination. So isogonal lines are lines joining places of same declination. So lines joining the places of same declination are called isogonal lines. Then what is agonic lines? Agonic as well as agonal lines. These are lines joining places of zero declination. Agonic or agonal lines are lines joining the places of zero declination. Lines joining the places of zero declination are called agonal or agonic lines. Okay, how can we measure dip at a place and what's the importance of, sorry, not dip, what's the importance of declination? The main importance of declination is in the navigation purpose. So importance of declination comes in navigation purpose, navigation. And so I can say we can use a compass needle to measure declination at a place. A compass needle, Malayalam vadakku nokkiyendram, Malayalam is a vadakku nokkiyendram. A compass needle can effectively measure declination at a place. I don't mean the GPS and all, but the older technology which were used for navigation purpose. So what I'm coming to say is that the declination at a place can be determined by means of a compass needle. Okay, you can use a compass needle for the measurement of declination at a place. Now this is what you have to understand, and the importance of the idea of declination comes in the navigation purpose I am saying. Now we move to, so this is the first element of Earth's magnetic field, declination. It is very important in the board exam point of view, as many portions from this chapter is removed. There is a lot of possibility of asking questions based on this particular portion, let me tell you. So declination, what is declination? I repeat, it is the angle between the geographic meridian and the magnetic meridian. It will vary from place to place, also you will understand. Now moving on to the second element of Earth's magnetic field, that is called a dip or inclination. Dip or inclination. Now let us consider Earth. This is the magnetic north pole. This is magnetic south pole. And you can see that this is the direction of the magnetic field lines around Earth. Now if I draw a line like this, this line is called a magnetic equator. Magnetic equator. Okay, this is again magnetic lines. So outside the Earth, it is from magnetic south to magnetic north. Now if I plot a tangent here, I can see that this magnetic field here is likewise nearly vertical. Vertical means perpendicular to the surface of Earth. It is nearly vertical here. What about at the north pole? You can see that this is the direction of the Earth's resultant magnetic field. Here also it is nearly vertical, you can understand. So first point I want to say regarding the Earth's magnetic field is that at the poles, Earth's field is nearly vertical. At the poles, at the magnetic poles I am saying, it's not the geographic poles. At the magnetic poles, the Earth's field is nearly vertical. Now if I plot a tangent here, what will you say about the field here? This is the direction of the magnetic field here. This is the direction of the magnetic field here. So that is at the magnetic equator I am coming to say. At the magnetic equator. So what is say at the equator? At the equator, as you can see here, at the magnetic equator, as you can see, that the field is parallel to the surface of Earth. Field is parallel to the surface of Earth. Field is parallel to the surface of Earth. Parallel to the surface of Earth. Parallel to the surface of Earth means what? It is nearly horizontal. At the equator, Earth's field is horizontal. Earth's field is horizontal, let me tell you. At the equator, you can see that the Earth's field is horizontal. Now the question I am asking. Suppose if I take a point somewhere here, how will you represent Earth's field? You will represent Earth's field like this, that is tangent dot to which. Now here I can say, okay, this field can be resolved into two components using vector resolution. This is one component which is parallel to the surface of Earth, which I will represent as HE as given in the NCERT book. This component is parallel to the surface of Earth, that is HE. Parallel to the surface of Earth, that is HE. Now this component is perpendicular to the surface of Earth, that is ZE. This component is parallel to the surface of Earth, as we said, it is HE. So I will tell you, HE is the horizontal component. HE is the horizontal component of Earth's field. ZE is the vertical component of the Earth's field. What is HE? HE is the horizontal component. Why it is called horizontal? Because it is parallel to the surface of Earth. ZD is the vertical component of Earth's field. Why it is called vertical component? It is perpendicular to the surface of Earth. Now if I plot this angle as delta. This delta is what? What is delta here? Delta is the angle made by what? The Earth's resultant magnetic field with the horizontal component. Delta, I repeat that sentence. Delta is the angle made by Earth's resultant magnetic field with the horizontal component. Which means what? So that angle delta is called dip. And I tell you the definition is very important. It is the angle made by Earth's resultant magnetic field with the horizontal component. Angle made by Earth's resultant magnetic field with the horizontal component is what is called a dip. Now, looking at this figure, I am just taking a copy of this figure, I am saying. Okay, I have just taken a copy of this one. Now, what I will do is that I will remove what is not relevant for me. Then, I am just going to rotate this thing. Okay, how can this. Now see here from this figure, what is cos delta is equal to? Cos delta. You can see figure and tell me what is cos delta here? Cos delta. You can see cos delta is adjacent by hypotenuse, which is HE divided by B, or HE is equal to B cos delta. This is very important. Now then another thing I would like to ask is, what is sin delta here? Sin delta is equal to, what is sin delta here? Sin delta is equal to ZE divided by HE, which implies HE, not HE, sin delta is ZE by B. ZE divided by B, which means ZE is equal to B sin delta. Now from figure one more thing you can find out, that is tan delta. Tan delta. What is tan delta here going to be? ZE divided by HE. Tan delta is ZE divided by HE. Now, sorry, I want that part. Let us take the first part here. Take the first part. At the poles, Earth's field is nearly vertical, as you can see here. That means at the poles, HE is equal to 0. Nearly vertical means horizontal component is absent. H is called horizontal component, Z is called vertical component. At the magnetic poles, the horizontal component is absent. Which implies B is equal to ZE, which is equal to B sin delta, right? Or sin delta is equal to 1 because Z is equal to B, or that implies delta is equal to pi by 2. What does that mean? At the magnetic poles, the value of dip is pi by 2. At the magnetic poles, dip angle is pi by 2. Now at the equator, in the similar way we can say at the equator, ZE is equal to 0 because we told it as horizontal. Now which implies B cos delta is equal to HE. But HE is already equal to B because at the equator ZE is absent, which means these two coincide. Or cos delta is equal to 1, delta is equal to 0 degree. So these two are very, very important points. Let me tell you, the value of dip at the equator is 0, value of dip at the poles is pi by 2. At the equator it is 0, at the poles it is pi by 2. Generally by convention we take dip in the towards north pole as positive and that towards south pole is considered to be negative. The value of dip in the north pole is positive and that in south pole is considered to be negative, because we had a similar question in 2009 NEET paper where in the south pole dip is going to be like something minus 25 degree and the other one it is going to some plus 25 degree. That's the reason why I said so. So these are the aspects of Earth's magnetism, and let me tell you, this is very, very important. Now we will look into a problem very quickly. So this is example 5.9. In the magnetic meridian, the horizontal component of Earth's magnetic field is 0.6 gauss, which means what is given is ZE is equal to 0.26 gauss and the dip angle is 60 degree. Delta is equal to 60 degree. You are asked to find out what? Earth's magnetic field. You are asked to find out B. What formula shall we use in order to solve this question? What formula shall we use? We have the formula ZD is not ZD, is HE. Horizontally somebody is what is given. HE is equal to B cos delta. Substituting the values, 0.26 is equal to B into cos 60. We know the value of cos 60 is 1 by 2. This is B into 1 by 2. Or we will get B is equal to 0.26 into 2. It is 0.52 goes. This is the answer to this example 5.9. Now we are going to discuss the next topic, that is magnetization and magnetic intensity. Magnetization and magnetic intensity. Magnetization and magnetic intensity is another topic that we are going to discuss. Okay, let us consider a solenoid carrying a current, assuming it's a long solenoid. Let B0 be the magnetic field inside the solenoid. We can write from our knowledge it is mu0 Ni, or I will write it as mu0 H. What is H is equal to? Where H is equal to Ni. This is the cause of magnetization. N and I are the cause of magnetization. So we call it by the name magnetizing field. Okay, in the next equation what I will do is that I will insert an iron core. Which completely occupies the space of the coil. Okay, so that means I will keep doing this thing more. Okay, fine. Now the new magnetic field inside this one is equal to mu0 mu r Ni. Hope you understand this, because on introducing a core, the permeability of the core becomes mu, which is mu0 mu r. Now this can be written as mu0 mu r into h, or this is equal to mu h. We are learned mu r is equal to mu divided by mu0, relative permeability. Okay, this is equation number 1. This is equation number 2. This is the total magnetic field inside the solenoid right now. Total magnetic field inside the solenoid right now. Then my question, what is the magnetization of the material? If I write it as B0, this is the magnetic field associated with the solenoid, plus Bm, this is the magnetization of the material of the core. B0 plus Bm is equal to B. Or I will say Bm is equal to B minus B0. B minus B0. So from here I can say, from B and B0 you have so many times to take common factor. This is mu0 H if I take. You will get it is mu r minus 1. According to the principle of homogeneity, mu r is a dimensionless quantity, because one has to be a dimensionless quantity. Already we know mu r is dimensionless quantity. So I am going to write it as mu0 chi h. In that situation you will say chi is equal to mu r minus 1. And the term chi is called magnetic susceptibility. Chi is called magnetic susceptibility, and the value of chi is equal to mu r minus 1. Now I can also say Bm is equal to mu0 into capital M, which implies capital M is equal to chi into h. Chi into h. Now what is chi? I am going to write again. So M is equal to chi into susceptibility. H is equal to Ni. What is N? Number of turns per unit length into I. Now I'm going to do one thing. This is chi into N I A divided by A into L. Because L was already there, I multiplied with A. Here A stands for area of cross section. Now NIA we know that it is magnetic moment. So chi into NIA in this context represents induced magnetic moment. So M can have another formula. This is induced magnetic. So it is induced magnetic moment. Divided by what is A into L? Area cross section to length is volume. So this is another definition of magnetization. That is induced magnetic moment per unit volume. And let me tell you, A and M are having same dimensions, right? A and M are having same dimensions, and their SI unit is ampere per meter. The SI unit is ampere per meter for both of them. So what is M called? M I didn't call. M is called the intensity of magnetization. So M is called the intensity of magnetization. Okay, so hope this derivation is clear to you, because this is slightly out of, this is different from what is given in the NCERT. I felt that derivation being a bit confusing, so that's the reason why I prefer for this derivation. Now we will look into another problem. This is an example 10 from NCERT. It's a very, very important example. 10 I don't remember exactly the number. A solenoid has a material of relative permeability 400, that is mu r. Mu r is equal to 400. The windings of the solenoid are insulated from the core and has 1000 turns per meter. 1000 turns per meter. If it carries a current of 2 ampere, find H. We have the formula for H is equal to Ni. That is 1000 into 2, which is equal to 2 into 10 raised to 3 ampere per meter. Now the second thing we need to find out is susceptibility chi. We have the formula, it is mu r minus 1, which is equal to mu r minus 1 is 400 minus 1, that's equal to 399. Now what is the next thing? The magnetic field B is equal to mu 0 mu r into H for pi into 10 to the power minus 7. Mu r is 400. Now H is how much? 2 into 10 to the power 3. So this is 4 into 2 is H. 8 pi into 10 to the power minus 2 multiplied by 4. So 8 pi is approximately 25. 8 pi is approximately 25. 25 into 4 is 100. This is 1 Tesla. What is the last branch? The induced current, which is Im. So here I will use the formula. H is equal to, M is equal to chi H. M is equal to chi H. So answer is different. So you have to do according to what is given in the NCERT. Here I am going to write this small n into Im. So M and H are dimension is same. This is equal to chi into Ni. Now n and n can be cancelled, which means Im is equal to chi into Im. Chi is given us 399. 399 into 2, that is equal to 7. 798 ampere. The induced magnetic current is 798 ampere. And this is the end of this session. Hope you understand this chapter, because the chapter is only this much. You can ask your doubts. Thank you.